She's a third-year PhD student at the Commissariat à l'énergie atomique and aux énergies alternatives at the Cadarache Center in the service of technology des composants et des procédés in the laboratory of the sodium risk treatment. Her PhD research aims at providing a numerical tool that enables users to describe the structure of the jet as a function of the flow rate of the gas leak. The developed model is implemented in CANOP, which enables users to generate the adaptive mesh refinement and to calculate in parallel. So without any further ado, Mr. Chen, I will give you the floor. Thank you again for this webinar presentation.
Okay, hello everyone. First, thank you for this short introduction of me. And thank you everyone who comes to listen my talk. And I want to add one more information about myself. Is my PhD defense will take place on the 2nd October, and you are welcome to attend my PhD defense as well. So during this 3-year PhD research, I work on the modeling of compressible multiphase flow. And today, I'm going to talk about my research application in SFR, security study of sodium gas heat exchangers in frame of sodium-cooled fast reactor. I'll begin my talk by introducing the context and the objective of present work, including ASTRID Project and its innovative concept, SGHE design. Then I'm going on to highlight the development of present work, such as a predominant physical phenomenon, mathematical model for multiphase flow, and its numerical methods, etc. I'll continue by briefly discussing some results in part 3, including validation tests and the application of under-expanded gas jets modeling. Finally, I'll finish my talk by the conclusion and perspectives. Now, let's start with the introduction of the ASTRID project. French nuclear policy toward a more sustainable nuclear energy, the closed field circle. It requires a circle based on fast neutron reactor. French fast reactor program priority is given to the SFR, while the ASTRID project. And the main objective of the ASTRID project is to provide a demonstration on the operability of SFR industrial reactors. And so as a SFR, or we say a straight tap reactor, the main favorable features are, first, the whole primary loop is contained in main vessel, including the core and the primary pumps, etc. Second, the good properties of sodium, such as a large boiling merge, for example, at a pressure of 1 bar, the temperature from around 100 to 900 Celsius, the sodium remains in liquid phase. Third, SFR has a high thermal inertia in case of loss of main heat sink due to the large quantity of primary coolant. And besides, there is no xenon effect, no need of soluble nutrient poisons. And collective dose on a pool tap SFR is very low compared to PWR. And here, the feature that I want to emphasize for the present work is the immediate system provides an extra containment between the primary loop and the environment. It avoids any radioactive material outlined from the primary vessel. The intermediate heat exchanger transfers the thermal power from the primary loop to the third one, which is the power conversion system, PCS. In the frame of PCS study for ASTRID reactor, in order to improve the safety, especially sodium water reactor risk, there are two systems started in parallel. First, the classic one is water steam PCS with steam generator. The objective of this system is to improve the robustness of steam generator relative to the sodium water reaction, and the sodium water reaction knowledge and its modeling, etc. So the question is how to minimize the sodium water reaction risk in SFR. So this question leads to the study of another concept, the gas PCS. In the Brayton Circle gas power conversion system, sodium gas heat exchanger (SGHE) using the initial gas replaces the steam generator, and it is CEA in charge of this in its development. And this is also one of the main innovative options in investigation for ASTRID project. And our present work is in the front of the SGHE development. And this development requires different fields of studies. First, the components relies on three disciplines in strong interactions. First one is general design. The general design study, which proposed a three-dimensional view, taking into account the technical constraints. Second one is the thermal hydraulics. It allows to define heat transfer surface, taking into account the efficiency and the heat exchanger technology. The last one is the thermomechanical analysis. It allows justifying the design, and this design process is iterative, and is coupled with resources and developments of materials and physical chemistry. So constraints from regulatory aspects and the use of sodium should be also considered. So finally, both the design and manufacturing should be validated through a number of phases at different scales before proposing SGHE in its final version. So the general design of SGHE is shown on this slide. The SGHE concept is a component power unit of 180 megawatt thermal. It means two components, each secondary sodium loop. The principle of this design of SGHE is based on a component integrating 8 elementary module of compact plate heat exchanger into a pressurized vessel, which also plays the role of inlet manifold. And these design options aim at maximizing the compactness and minimizing the pressure drop, minimizing the sodium inventory in the components, and limiting the thermomechanical stresses, etc. And a test of 40 kilowatt SGHE was carried out in CEA, and the efficiency can reach up more than 37%. So in this design, what I want to emphasize is the nitrogen is chosen for the tertiary loop, and the pressure of the nitrogen is 180 bar, and well, the liquid sodium is 5 bar. So in an accident scenario where the heat exchanger wall cracked, this huge pressure difference across the wall could lead a gas leak submerged into liquid sodium. And according to the previous stories in CEA, the gas leakage can be classified into several types by the crack size. The one is a subsonic jet, noted under expanded gas jet. This is the one who covers all physical phenomena of different gas leaks. So particularly in safety analysis, the structure of underexpanded gas jet enables to develop the acoustic methods to detecting these gas leaks. For example, based on the bubble distributions and Mach disk. So what's the Mach disk? Okay, as we can see, this is the picture of general structure of an underexpanded gas jet submerged into a liquid. And as we can see here, this is the Mach disk, which separates the flow into regions. In subsonic region, upstream of jet, and subsonic region, downstream of jet. Okay, let's come back to the safety analysis. The acoustic methods requires dedicated knowledge of jet structure. So in order to achieve this study, at different physical phenomena, the CEA carried out a number of collaborations with the other research institutes and centers. For example, at the point of viscous effect inside of nozzle flow, we have collaborated with the IMFT in Toulouse, France. For the study of compressible flow, particularly for the barrel shock and Mach disk, we did work with IMFT, IUST in Marseille, France, ANL, and in USA. And for the acoustic detection for liquid noise, we have collaborated with KTH, liquid droplet behaviors in subsonic flow. We have worked with IUST. They did experiments for the CEA. And concerning the bubble distribution study, the experiments of nitrogen gas injected into water and liquid sodium were carried out on a snake facility at ANL. As we can see, this is the photo of a snake facility at ANL. So, in the frame of this work organization, the objective of present work is to provide a numerical tool to estimate the structure of underexpanded gas jet as a function of flow rate of gas leak. Okay, next I'd like to talk about the development of present work in detail, starting by development process. First, we started the development process with the identification of the physical phenomena, and it allows developing a numerical, mathematical model to describe this physical phenomena. And then we implemented this model into a numerical tool and carried out several validation tests to verify our mathematical model. Once the model and numerical schemes are validated, we applied the code into the underexpanded gas jet modeling and compared the results with the reference cases. And this process checked the agreement between the developed model and the identified physical phenomena. So some improvements could be done accordingly. So concerning the identification of main physical phenomena, the velocity inhomogeneity between two phases is studied firstly. Okay, first, Le Hormozy carried out experiments of nitrogen injected into water with a stagnation pressure of 20 bar and the nozzle diameter of 0.7 millimeter. And the results showed that the velocity difference between two phases could reach up certain hundreds meter per second. And besides, a previous PhD work of vivality in CEA carried out a numerical study of gas injection into sodium liquid with a stagnation pressure of 7 bar. And it shows the similar velocity difference as well. So this viscous inhomogeneity should not be ignored in our case. So our module needs to consider the velocity of each phase and the momentum exchange between both of them while integrating the drag force between continuous phases and displaced phases. So besides, in an underexpanded gas jet submerged into a liquid, as we talked previously, there are displaced phases region, bubbles, droplets, and their transition. So the evolution of bubble size depends on the pressure difference between the inside and outside of the particle. So as one objective of present work to track the evolution of displaced phases, bubble size evolution, the model needs to take into account the pressure inhomogeneity into as well. Okay, so as to viscosities, we did a numerical study of numerical study of monophasic underexpanded gas jet in a SGHE channel, and this work is published in last year. It's shown that the viscous effect inside of nozzle influences the structure of downstream offsets. For example, the curvature of the incident shock waves, particularly the Taylor-Cutler vortices due to the comparison between the centrifugal effect and the viscous physics effects in the boundary layer are observed. As we can see on the bottom picture, each impact produced by the underexpanded gas jets corresponds to a counter-rotating vortex pair, and these vortex pair are from the Taylor-Cutler instability. So therefore, it's very important to take into account the viscous diffusion in the pure phase in our model. Except these three predominant physical phenomena, we have checked that there is no chemical reaction according to the experiments carried out at ANL. And besides, there is no phase change in an underexpanded nitrogen jet into liquid sodium. This picture, this is we interpolated the state point into the phase diagram of nitrogen, sodium, and water. They are respectively in the purple, blue, and orange color. So these state points are obtained from the numerical study of monophase exchange in an SGHE channel. And from this, we can conclude that under the SGHE operation condition, there is no phase changing of nitrogen and sodium. Meanwhile, for the nitrogen into the water, there could be the phase change of water. So according to the previous study of physical phenomena in nitrogen jet submerged into sodium, we developed our mathematical model from the Baer-Nunziato model, which enables to model two velocity and two pressures. And the systems include momentum exchange via integrating the drag force between two phases and the viscous effects in the pure phase. And numerically, the Riemann problem for biphasic flow is solved by Husanov solver, and the model is interpreted into a Muschelkalk scheme. And now the question is there any other systems that we need to consider? So first, I want to show you a very interesting biphasic shock tube test. As we can see in this picture, in the shock tube, in the left chamber is filled by gas with a pressure of 180 bar, and the right side is filled by liquid sodium with a pressure of 5 bar. And this is the same condition with the SGHE operation condition. And the equation of state is Albert Nobel Stephen gas for both of them. Okay, first let's see the results. This is the profile of velocity. In the right side of shock tube, where the gas is absent, the velocity of gas, noted fluid 2, reach about 1,000 meters each second. The same result is observed in the pressure profile. For example, on the right side here of the shock tube, where the liquid phase, noted fluid 1, is absent, and there is huge change in no physical of pressure. And this observation is no sense in physics. Therefore, we need to add something to correct these non-physical effects of the fictitious phases in the pure phase. In the pure phase, so the solution that we find is the velocity and the pressure relaxations into the model. So, and this is the result obtained with the model adding the velocity and pressure relaxations. We can see that the no physical effects is corrected. So for the next step, numerically, for the under expanded gas jet modeling, in the displaced phases and shockwave regions, we need the mesh well refined. And in the other regions, we don't need the mesh be refined like this. So a numerical tool which enables to generate adaptive mesh refinement fits our need. So we interpreted our model into a numerical tool, CANOP, named CANOP. And there are two layers in CANOP. The low-level layer enables to carry out a cell-based adaptive mesh refinement and computation in parallel by integrating the P4 REST library. And as we can see, this is an example of AMR generated by the present code, and it's controlled by the density gradient. It means that mesh is well refined. In the well, the density gradient is very strong. And in the high level layer, it enables us to implement the numerical schemes while the finite volume method, particularly for solving the problem in fluid dynamics field. So in more detail, the commons function in CANOP are in charge of the term iteration, mesh adaptation, cultural management, connectivities, etc. Based on these common functions, we can develop branches for each problem by defining the user date, numerical schemes, boundary conditions, initial conditions, etc. And the present work develops a new branch to solve the problem of compressible multiphase flow, particularly for the application of underexpanded gas jet into a containment channel named superbifluids. So, and then we can send our testers to Idris machine. This is an institute for development and resources in intensive scientific computing, which enables to launch the intensive computing. So now let's move on and discuss results. Including model validation and its application of modeling of underexpanded gas jet. There are 3 steps in the calculation strategy. First, we focus on the validation of convective part by the two-phase shock tube test. And then validation concerns of source temp, including viscous diffusion in pure phase and the momentum exchange between the continuous phases and the displaced phases. Once the validation is finished, we applied the model to carry out the modeling of underexpanded gas jets. So at the point of convective part validation, I'd like to show you an example of multi-phase flow shock tube test. The initial condition for the fluid one are identical for 2 chambers, excepting the volume fraction. In left chamber is 0.7. In the right chamber is 0.3. For the fluid 2, the high pressure is located in right chamber. It means that the shock waves will propagate from right side to left side. Okay, this is the comparison between the exact solution and the numerical results of fluid 1. Yeah, sorry. The discontinuous initial condition of fluid 2 causes the shock waves and expansions for the fluid 1. And besides, we can see that the numerical results agree well with the exact solution. And for the fluid 2, the shock waves propagate towards to the left side, and we can see the contact surface and volume fraction contact surface are well produced by comparing with the exact solution. So in conclusion for this part, according to a number of validation testers, we can conclude that the convective part is validated. For the viscous effect validation, we did a classical test, Poisson flow. The gas flow enters from left inlet into a channel of 0.2 meter. And here are the numerical results compared with the exact solution. I want to explain here the key noted L, for example, 3.8 means that the minimum and maximum level of AMR is 3 and 8 respectively. And we can see as well the numerical results agree well with the exact solution. It allows us to check the integration of viscous effect. Now let's focus on the momentum exchange. At this point, we did the test with a gas-water mixture of the mixture that the velocity of each phase is different. The figure on bottom on this slide shows the velocity and pressure evolution over time. The momentum exchanging between two phases make their velocity tend to the same over time, and the new pressure profile for each phase. So as a conclusion, the system of momentum exchange is validated. Overall, the developed model and its numerical scheme are validated. And so in the following slide, they are applied into the modeling of under-expanded gas jet. First, I want to show you one comparison with the experiment. In this study, the nitrogen of 180 bar was injected into water of ambient pressure. And this is the generation of gas jet over time. And comparing with the experiments, the jet is in a mushroom shape during the generation phase, and the vortex behind front surface of jet are well produced. These phenomena are well observed both in experiments and in numerical results. Let's compare the results in more depth. First, I want to present the main character in an underexpanded gas jet, Mach disk. In the picture of left side, the picture noted A is obtained from the monophasic jet. The picture B noted B is obtained from the biphasic jet. And very interesting difference of Mach disk between the two cases is observed. In the biphasic jet, several shock cells are produced instead of one only shock cell in monophasic jets. One reason is because the gas with very high velocity injected into liquids, which is at rest. It causes the entailment of liquid bad gas, and this part of liquid doesn't participate into the formation of Mach disk, and this is why the Mach disk of biphasic case is separated into several cells. And in addition, we compare the volume fraction results with the experiments. Okay, we can see there is a difference between both of them in bubble region. Here, it means the volume fraction is close to 1. Because this is the free gas jet. In this case, the turbulent effect in bubble region becomes more significant. Meanwhile, the present work doesn't integrate the turbulence model into consideration, because our final objective is to model a gas jet in a channel with a width of only 3 millimeter. The effect of turbulence can be ignored in such a small channel. So Nevertheless, of this difference, this test shows the capability of the code to reproduce the main structure of biphasic under-expanded gas jet. It allows us to apply the code to model the gas leak in a SGHE channel. For this modeling, the nitrogen jet injected into a sodium channel from a reservoir. The initial conditions are obtained from the general SGHE design. The vessel of sodium channel is 3 millimeter, and the crack size in this case is 0.5 millimeter. In this study, some hypotheses are considered. First, the size of each displaced phase is supposed to be uniform. Second, the fragmentation of displaced phases owing to the shock waves and its reflected waves is ignored. Third one, the interface properties are considered homogeneous in whole region. I will explain more at this point. So in the present work, there are terms relevant to the velocity and pressure of displaced phase in interfaces. However, in our case, there are two types of displaced phases, bubbles and droplets. The interface properties depends on type of displaced phase, actually. But in the present work, we suppose that the interface properties are identical in the whole region. And that's the one we don't take the turbulence model into consideration. So let's see some results. First, this is the velocity profile of gas in function of injection direction, X. And the profile is compared with the monophasic one. For the monophasic jet, the straight discontinuity of velocity profile stands for the Mach disk localization. Meanwhile, the Mach disk localization for biphasic jet is not so straight as the one of monophasic, because the flow of mixture of because the flow is a mixture of gas and liquid sodium downstream of jet, and the gas liquid mixture makes the sound speed profile more smoother. It provokes the propagation of shock waves smoother, and this is why the localization of Mach disk is smoother for the biphasic jet in a SGHE channel. Besides, as we can see here, the flow behavior near to the nozzle, here is the nozzle, is in S shape. This is due to the strong channel containment, and this containment creates the vortex near to the nozzle outline. And the flow behavior leads to the volume fraction distribution. The bubble are advected throughout the channel, and it means that it's possible to provide the data for acoustic method development based on the bubble distribution. And the following work is to carry out modeling of underexpanded gas jet with different nozzle sizes in order to study the jet structure in function of gas flow rates. On the other hand, the future validation experiments will be performed on Aix 2 facility in CEA Cadarache, following the present work. Finally, let's review some key points from the present work. As conclusion, first, a biphasic flow model integrating main physical phenomena of an underexpanded gas jet is developed. Our model enables to model each velocity and pressure for each phase, model the momentum exchange between two phases and viscous effect in pure phase. We add also velocity and pressure corrections of the fictitious phase. Second, the model is implanted into a numerical tool, CANOP, and its capability to reproduce different two-phase flow configurations is validated. And the results of modeling of underexpanded gas jet in a SGHE channel are promising. So the achievement of this work enables to schedule following work. So at the point of perspective, first, in order to improve our mathematical or numerical model, first we can take into account the interface property in function of different displaced phases, droplets and bubbles. And second, we can take into account the size inhomogeneity of displaced phases as well. And experimentally, experiment equal to will be carried out to check the flow behavior in a channel. And the experiment of gas jet in SGHE character may be carried out in the future. So that's all of my talk, and thank you for your attention.
Thank you very much. If you do have questions, go ahead and type those into the Q&A pane at this time. While those questions are coming in, we'll go ahead and take a look at the upcoming webinar presentations. In August, a presentation on lead containing mainly isotope 208, a new reflector for improving safety of fast nuclear reactors. In September, a presentation on the Gen 4 coolants quality control. And in October, passive decay heat removal system. Does anyone have questions? If you do, you can go ahead and type those into the Q&A pane now. As a reminder, today's webinar presentation is a volunteer communication event. Thank you for those who've sent your selfies. If you still want to participate and haven't sent a selfie, take a picture of yourself with the presentation in the background and email that to boats@highdesertcs.com, and we'll collect those pictures into a mosaic and post those on the GIF website. Are there any questions?
Okay. I don't see the Q&A pane. Is there some problem of the efficiency? This one.
Here we go. There's a question that asks, what does the size of the E-ropelet influence the results?
Excuse me, I I didn't hear you very clearly. Could you please repeat your question?
Sure. There's a question that says, what does the size of the eroplet influence the results? I'm going to,
So your question is concerning the comparison between the experiments and the results, numerical results, right? Okay, size of the...
do you see it now?
Yeah, I see that. Yes, I see the question. Okay, actually, the state point is obtained from the monophasic case in ECSG channel, and we are compared our non-spaced. And we all compared our biphasic results with the experiments. And now, at present work, we considered the size of displaced phase is uniform. It means we considered all the bubble has one size and all the droplets have one size. So it means we didn't consider that the influence of fragmentation of the displaced phases on shock tubes and its refracted shock waves from the containment of channel. And for the results of free jet, as we can see that the results compared with the experiments carried out by Koleok, we have a difference in the bubble regions. Well, in this region, is the surface tension is more significant. It means we need to take into consider the displaced non-uniform size of displaced phases.
Thank you.
So for the next step, we'll take this phenomena into consideration.
Do you have any information that you can share on the progress of the ASTRID project? I'm sorry.
I'm sorry. I'm looking. I'm reading the question on the QA part. Could you separate? So can I ask you this question firstly?
Sure.
Okay. Okay. Could you share some progress of the STCP project? Okay. This is a very interesting question concerning the development of STCP project. Okay. What I know is At the first, according to the French French energy policy, we start the project ASTRID in order to demonstrate SFR industrial reactor. And at the beginning, the power of design is 1,500 megawatt thermal, and then according to the change of policy, the new street is proposed, and the power is reduced to 4,000 megawatt thermal, and now we say it's more than a program of development of SFR, and besides of that, as I'm a PhD student in CEA, so I focused on rather science than the project development. So maybe I can answer you this question in details by emails. So send me email.
Excellent. How is the pressure for the nitrogen established? Does your work suggest any modification to this pressure or the sodium pressure?
How is the pressure? Okay. Okay. This pressure. Okay. This design create is including multi studies in different fields, and the main objective for the pressure design is to minimize the loss on drop loss on gas system, and we compare. I think there was a PhD study concerning this research, and avoiding I think it compares. I can't remember really clearly, but it compares the operation efficiency and the material constructs and manufacturing process and so on. They fix the pressure for SGHE of 180 bar. And at this point, we can avoid saving about 20% of pressure loop of the current heat transfer zone. And this is and I think if the pressure more than 180 bar and the efficiency increases not very evidently. So this is the best point, best function point. And okay. No, I'm sorry, I didn't work on the study of the design of the pressure of sodium gas heat exchanger. I just did the modeling of gas jet into a sodium channel according to the general design of SGHE. So concerning this question, modification to this pressure and all the sodium pressure, maybe I can ask my colleagues and respond to you in detail by email later.
Thank you. I think we got the questions and the comments that are there answered. The webinar recording of today's presentation and the slide deck will be posted on the GIF website. If you'll just give us a few days to get that uploaded, we appreciate your patience. And I don't see another new question coming in.
Me neither.
Again, I want to thank you for your efforts in putting this presentation together and taking the time to present today. It is really greatly appreciated. And thanks to everyone who did attend, and I have received several selfies, so I appreciate that as well.
Yeah, I would like to thank you so much, Fang, for the good presentation, and I wish you all the best for your PhD defense in October.
Thank you. Thank you. Thank you, everybody.
Okay, so I guess we can finish the session, Bertrand.
I think that's it. Yeah, I think we can conclude. And
okay.
There's one question here. Your results appear to be strongly dependent on the pressure difference. Can you specify the regime and the validity of your results?
Okay. First, in order to the validation, and first we focus on the main structure of an underexpanded gas jet. It means the mag disk that I talked much previously. And so in this case, I show you this mag disk distribution, and we compared these characters of mag disk with the experimental correlations, and it shows a good agreement of the mag disk diameter. And then we focus as well of the flow behavior in the channel at the moment. For example, as we can see, there is a vortex near to the nozzle inlet, and the flow behavior is in S form. Besides, we checked as well the velocity and the velocity and pressure and the other profiles in the channel, compared with the experiments and the previous study of monophasic jets. And why we did we choose the pressure difference 180 bar and 5 bar, and 1 bar for the free jet. This is a reference to with the experiments and SGHE general design.
Interesting. The question is why the title is security study, not safety study. Could you explain a little bit?
A little. Okay. Okay. I think I confused with the security and safety study. In fact, it's more than a safety study than the security study. I agree with you. So I think this is maybe I made a mistake with the security and the safety study. Yeah.
Just a difference in language there is all.
Yeah. I'm a little confused, I think.
So does your model work as the nitrogen system depressurizes and the sodium pressurizes, or is your model only producing steady state results?
Okay. Yes. And depressed and sodium priced. In whole modeling region, and nitrogen and the sodium are full compressible. Both of them are compressible. It means nitrogen and sodium liquid are considered as compressible fluids, both of them. And our model produced steady state results, and as well the unsteady results over time. Yeah, not only in the steady state results. Now, as just like I show you that the generation of gas jet, generation phase of gas jet compared with the experiments on the over time, and the steady state results that you saw in the slides at the end of the presentation. The steady state is obtained by the time averaged over time. Yeah, we say.
Thank you. Again, thanks everyone for your participation today. And with that, I think we will conclude today's presentation and wish you all a farewell. Thank you again, Fang. It was a very interesting presentation.
Thank you. Thank you, everyone.